So yeah, this is this deep dive. It's actually going to be somewhat more of a high level because like the deep dive would take an hour or two, and I want to make this pretty quick. But yeah, for people who don't know, the FVM is the Filecoin Virtual Machine. Internally, it does not actually implement a new virtual machine. It actually uses an existing WASM or WebAssembly VM called WASMtime, but in theory, you could use any WebAssembly VM you wanted to, just based on WebAssembly. For some terminology, before we get confused, the FVM, again, is the Filecoin Virtual Machine. FEVM is the EVM on the FVM. So this is what we call our version of the EVM that we're going to be introducing in February of next year. An actor is a Filecoin smart contract. It's based on the concept of the actor model. In Ethereum, like you call into the actor. In Filecoin, you send to another actor, and then you receive back a response. This right now it's still very much calling based, but in the future we really want to add more asynchronous operations and some parallelism. This is kind of be covered later in the beyond section. But actor model like also captures the fact that Filecoin actors tend to be a little more complicated than Ethereum contracts. They do a lot. They're basically just real programs. Okay, interplanetary linked data. I don't know how much you guys know about that. Some people know a lot, some people know very little. IPLD is a very, very important system we build on that allows us to abstract over different types of Merkle-linked data structures. It's one of our secret sauces to building a lot of really cool things. Right now, you can't see too much of this, but for example, like we had, what was it called? Optimistic window post. This was made possible by using IPLD. If we had used anything else, it would have been really, really hard. But because we use IPLD into the covers, like we were able to snapshot certain data structures and just like sort of keep them around for a bit so we could check historical state. Without IPLD, we would have had to like copy data structures very, very carefully, like avoid touching things, and like it would have been really, very painful. But this made it really easy. And finally, WASM WebAssembly. It was an assembly language made for the web, but we were using it because it's designed to run like in a very like sandbox environment with no trust. It's very easy to also like to sort of statically analyze WebAssembly code and to instrument it. So we're doing that. We're using that for gas accounting. It's very, very structured. So most assembly is kind of just like, well, you have some assembly, whatever, you can jump anywhere. WebAssembly is more like an AST. It's actually a Lisp under the covers. Yeah, it's the background. Fundamentals. So as I was saying, the FVM is built on a WebAssembly VM. This gives us near native performance. WebAssembly has very, very good performance, primarily because it actually compiles down to native bytecode, and they play some weird games with addressing and what's it called, and address spaces to make it so they can actually align most of their pointer checks. So you can kind of just effectively like compile these untrusted programs into native code and just run them and know that they can't do anything bad. This also enables us to do like good static analysis. It enables other people to audit code. So one of the cool things here is in the FVM, you have to import your syscalls to declare which ones you import. So if it's some kind of dangerous syscall, you can actually tell if someone's importing or not importing it by just looking at their imports. In the EVM, you kind of scan the bytecode and hope that you find the right bytecode, but you couldn't, yeah. But it's hard to be sure about things. Okay. Another part about the FVM is it's designed to be a hypervisor. Basically, what I mean by hypervisor is like it's an underlying machine that runs other machines on top of it. So we are currently running the built-in actors, but right now we're building the EVM, and we really want to make this so people can sort of drop their own system in on top of the FVM, because that then enables us to kind of like borrow other ecosystems and really play nicely with everything else. This is just the theme at Pluggable Labs you may have seen, where we try to like just sort of integrate with everything. So if you've seen like multi-hash, multi-adder, like libp's transport system, IPLD, and all this kind of stuff, like it's all around like creating some abstraction over a bunch of different systems and allowing you to sort of use whatever you want and sort of take, it allows us to like interoperate with things. So we did this by, first of all, like compile the runtimes of WASM. Because it's WASM, it's very fast, so you can actually do this without like having, performance is not amazing if you're trying to run some foreign environment, but it's not like nearly as bad as it would be if you tried to do any other system. We're supporting user-defined addressing, so we can literally take another addressing system, kind of like put that inside a Filecoin address, and then take it back out. So it allows people to take their system as is with like address, basically address generation logic the same way. So like this, a lot of tooling will predict addresses. It'll say, okay, if I deploy this actor from this account with this code, like I will get this address. This allows you to actually like keep whatever guarantees you have in your old system the same when you import your system into Filecoin, if you do that. Finally, we're adding user-defined account types. So this is called account abstraction if you come from Ethereum. This will allow people to like sort of like use MetaMask or whatever they need with the Filecoin network. You can also, again, use other systems. It doesn't have to be Ethereum. You'll just be able to sort of like create your own account type and deploy that on the network, and people will be able to just like send messages to the network, transactions to the network using their favorite need or like their favorite system. Fundamentals, again, it's built on IPLD. This enables like really easy on-chain version snapshots. It supports pass-by-reference between actors. So this is a feature you don't get on, I don't think, any other blockchain really. Basically, in Filecoin, you can actually send an entire substate tree. It's like you send a pointer in a programming language. In most systems, okay, you could reference an entire actor or some other state. So like in Solana, you have like your accounts that have state, but that's like the granularity at which you can reference state. Here, like even within a single sort of atomic object, you can actually reference sub-objects and send them around with basically pass by reference, but copy on write semantics. So like I can pass you reference, you can't really modify it, but you can create a new version of it very cheaply and then send that back. This will be really important later for a lot of parallelism stuff because it allows us to sort of like spawn off a bunch of read-only parallel workers. They can do whatever they need to do, return their state, and then like the sort of the coordinator can then like commit the final results, which is something that's very hard to do in something like Ethereum where everyone just kind of has to write into the mutable state. Finally, it allows for user-specified data layouts. This means like basically users get to decide like what data goes next to what other data. So if they have data that's frequently accessed together, they can put that next to each other. Okay, that covers a lot of the details. This is the scary slide. This is how it actually works. So you can tune out for this next section. I'll wake you up in a few minutes. But I do want to like give some people here an idea of how this works so that when if they touch the code, they can understand this. Basically, that blue section is the executor. That basically is sort of one, well, I say block, actually that's wrong, tip set execution. So basically, for a single tip set, you have a single executor that executes all the messages in that tip set. It executes those messages on top of a machine. The machine kind of represents the state of the system and also the externs. This is how we interact with clients. So like the FVM is this Rust program right now, at least. We can have other implementations of other programming languages, but right now we only have one in Rust. But it doesn't implement everything. It doesn't have like a block store. It doesn't have a chain. It doesn't understand any of that kind of stuff. So instead, right now, it shells out to the client, so Lotus or Forest or whatever, to ask if like randomness or chain information or whatever. That's what the externs are. So that's how basically effectively a message, the executor applies messages to the machine. It does this using that sort of block over there, the call manager, the kernel, the invocation container, all that stuff. Basically what happens is message comes in, when you create a new call manager, this manages the single sort of call into the system. It's the call stack really. That then creates an invocation container to run your actor, your WebAssembly program. That then runs inside there. If we have the EVM, then we put the EVM inside the WASM, the little WASM section there. That can then call back out to the system through what we call syscalls. It's like on Linux. They look very similar, actually. You basically just call it these special host calls. The kernel then handles these, and if, for example, you're sort of sending to a new actor, the kernel will then call back into the call manager. The call manager will create a new kernel, which will create a new invocation container, and sort of go back and forth and back and forth and back and forth. And that's kind of the life cycle of a message, where you kind of go, you call down, creating a bunch of new invocation containers, then you destroy them as you go back up, and then call back down. So that's how that works internally. Then we just do this over and over and over again, once for each sort of top level message. Finally, this is built on top of an engine. We use WASM time as our sort of our core execution or VM, and we have some module caches and stuff like that. So that's this. Okay, now you can wake back up if you were not paying attention to this. And now I'm going to talk about FEVM, which is the next milestone. This is coming in February 2023. We already have, as Molly was saying, a testnet. It's very, very bleeding edge. It is missing a lot of important features that we are still working on. And some of the features are currently built with hacks. But like we have a plan, we have a testnet, and it's actually working. So the goal of FEVM is really to bring the entire Ethereum ecosystem to Filecoin. We're not trying to compete with Ethereum. We're literally just trying to say, hey, like there's all this stuff there. There are all these tools. Why do we have to like make our own things? Why can't we just use what's there? Because like we don't have the bandwidth, the capacity of the people to like build this stuff. Yeah, that's the main reason. The other part is that like this lets us sort of play a little bit safely. This means that, okay, we don't have to expose all of our fancy IPLE stuff right now. We get a bit more time to bake that and make sure we get it correct. Instead, we can expose like sort of battle tested Ethereum APIs first and let users use that. So the way we're doing this is basically we're compiling EVM inside of an FVM actor. Every single FVM actor, or sorry, every single smart contract or EVM contract will have its own separate FVM actor and its own separate FVM address with its own sort of separate EVM instance. This is fine. It's not it doesn't cost anything in terms of like state on chain because we content address the EVM actor. So basically, the actual actor is two CIDs, one which is the content ID. I didn't explain that. Basically, one hash that points to the EVM actor code and one hash that points to your current state. So it doesn't really cost us anything to sort of like create one instance of the EVM per actor. The next part here is we have Ethereum addressing through a new F4 address class. This is what I was talking about before. It lets us embed an entire Ethereum address inside of a Filecoin address. So like I can like go to Ethereum Tooling, get the address, embed it, use it, get some result out, get back in another Ethereum address, put that back into Ethereum Tooling, and all this kind of works. We're getting Ethereum accounts through account abstraction. This basically lets someone submit an Ethereum transaction through, actually, we're going to expose the Ethereum JSON RPC API on Lotus, at least that's the goal. And they submit their Ethereum transaction that way. We kind of like smoosh it a bit, make it look more like a Filecoin transaction. And then you can have an Ethereum account on chain that sort of like turns it back into an Ethereum transaction, validates the signature. But this means you can submit like native Ethereum transactions and it just kind of works. So all of your tooling just works. Yeah, as I said, a JSON RPC API in Lotus. This means, again, like MetaMask just works. We're using it right now. There's some hacks properly and stuff right now, but we're still working on fixing all of those. And then finally, we're introducing an Ethereum event system via a new FEM event system. For now, our events are going to be very bare bones. It's basically like, okay, you can write events, but we're not really going to worry about indexing them too much. We're hoping that in future releases, people will come up with good proposals for this, but the current proposal is very much like, no. We just write the events. People can use them for like tracking minor actor state and all this kind of stuff, but they're not, it's not going to be like the sort of the end goal. Okay. EVM inside the FVM. So basically as I said, we've compiled the EVM into WebAssembly. We've actually built our own EVM implementation. We based it off of, I think, something called evmodin, but we've rewritten everything basically at this point to make it try to make it as fast as possible. There's no special EVM support. That's really the goal here. Like we don't want to have any hacks or anything that says, oh, this is necessary for the EVM. We may have some kind of whitelist in Lotus for certain types of messages. This will be more of a minor decision though, and not a Lotus specific thing if we have to do this. But there are some edge cases around account abstraction that I don't really want to go into right now. Make it a bit complicated. But basically the goal is like we don't want to have any like, oh yeah, like this is only used by the EVM. It's like this EVM specific feature, and like instead we're trying to make this general purpose hypervisor where you can sort of put whatever VM you want on top of it, or users can even deploy their own optimized or whatever EVMs. And the final thing is, again, it's first class. It's Filecoin gas. They're all Filecoin, top-level Filecoin actors and accounts. There's no like sort of EVM sandbox that just sort of keeps the EVM world separate. It uses the native fill token. There's nothing special about that. As I said, Ethereum tooling. I think I've basically gone over all of this. There's no trusted bridges or translations anywhere. You basically just point your Ethereum tooling at Lotus and it works. As I was talking about, pluggable addressing. This is sort of the specifics. If you have an actor ID 1234, you can plug that in, you'll get F4, which is the address class, 1234 F, just as a separator, and then you get basically the Ethereum address. There's actually a little bit of a checksum after that, just to make sure people don't mistype things, but that's basically how that works. This, again, supports any Ethereum addresses. It supports like create to and create and all these other counterfactual interactions and like addresses that don't exist on chain interactions, all that kind of stuff. And as I was saying, the custom account types. This is MetaMask using Filecoin with some weird funky gas numbers because we had a bug, but we fixed that bug. Those are insane gas numbers, but yeah, basically, whatever. If you want to test this out, you can. This is bleeding edge. And when I say bleeding edge, I mean really bleeding edge. So like we are actively hacking on this. The network will be reset pretty frequently as we ship upgrades. But it's really cool to play with this because you can just plug your existing Ethereum tooling in with Brave and it just kind of does the thing. But yeah, that's GitHub in case you didn't realize. Or you can scan the QR code. Okay, native actors. This is what we are planning on shipping in around Q3 of next year. Maybe that's the goal, but like Q2, Q3, somewhere around that area. We still haven't nailed down the final dates. We're not going to promise anything until we have actually done our full road mapping. But I can say it's probably around then, but this is like the Steven who has not yet done his road mapping saying that, so you can't hold me accountable for that. Yeah, so this will allow you to deploy native WebAssembly actors for better performance. You can take advantage of all the IPLD features, and you can add new runtimes. The version that's shipping in February will let you deploy EVM or smart contracts, but it will not let you deploy new native WASM smart contracts for like security reasons and like just API stability and stuff like that. It gives us more room to sort of finalize some things, but ship programmability now before we're done finalizing those things. Beyond, this is the fun part. So like, up next, after we actually get data programmability, we'd love to look into things like parallelism. As I was saying before, parallelism, like IPLD makes parallelism, like at least certain kinds of parallelism fairly easy. In terms of parallel processing of messages, that would require some more thought into how we process transactions in general. But like in terms of like parallel workers, where like some single actor could spawn off a bunch of parallel threads and like let some work happen in the background, that's actually fairly straightforward. There's also been a lot of talking about the FVM and the Lotus and actors teams about on-chain task scheduling, or cron, basically user accessible cron. No other chain really has this, but we really want a way to like sort of schedule new tasks on chain sometime in the future and have those automatically executed. We think this would really unlock a lot of cool use cases. We've also been talking a lot about like on-chain reactive programming reacting to events. This is something I don't think anyone else can do either. Most systems require some kind of like Oracle, something off-chain. This is where we'd like to go. And yeah, I mean, hierarchical consensus is not our team. This is the, I guess it's now called interplanetary consensus. But yeah, the FEM is really looking forward to supporting this. But yeah, that's really beyond. So that's it for my talk. I don't know if we have time for questions, but. Mike.
What's up? Right. So I think all of us support FVM. This is really awesome. As a storage provider, I think one of the things that we care about is that we are able to prove our data. Mm-hmm. One of the really annoying things is when you have these spikes of gas when the base fee goes up. And it's faster than your daemon can actually, reset or like up the gas until you actually get your messages on chain, meaning that we start losing our window post. I just want to make sure, because the interplanetary consensus here was also set for Q3, I think, something like that.
Integration into mainnet.
Yeah, exactly. Which means that we won't have the sharding and that kind of stuff in place, or maybe at the same time. So I just wanted to make sure that, on FVM, that we don't deploy something to mainnet that is actually, I know that we are using the Filecoin gas model and it has been like calibrated, but still that we don't have something where you put on some FVM and now you start to make these massive congestions of the mainnet network, because that would basically kill all our storage proving.
Yeah. That's a very good point. So at the moment, we don't think, like basically, we know that there's a fair amount of loose capacity that's not being used by, it's basically like, it's been taken up right now by sort of like an unaggregated sector ceiling. But if the chain or usage goes up, a lot more sectors get aggregated. We have not done the numbers on exactly how that's going to happen. We have another team working on that right now. I know CryptoEcon is thinking about that. We also have like some ideas of how we could create some kind of like multi-lane system if we need to. This would probably be in a subsequent upgrade. It's kind of like we don't actually know if it's worth it, or it's not if it's worth it, but like if it's necessary, and we don't want to delay programmability for that. The other thing I do want to note here is that this is a very different situation than like December several years ago when like gas was through the roof. Because in that situation, basically, the storage providers were paying for all the gas in the system, which was just a really bad situation to be in, because if the gas is through the roof and storage providers are paying for all the gas, then they're paying for all the gas. But in this case, if the gas prices go way up, that's going to be because other users are coming into the system to pay for the gas. And these users are buying this gas probably from the storage providers, mostly, I assume, because they're the ones getting the block rewards. There needs to be economic modeling here, where basically where the money would come from and how the flows would go. But effectively, as long as really over 50% of the network is being used by other parties, then the storage providers basically should fine that they get some block rewards, they spend some on themselves, and then sell some to cover the gas. It should be basically a wash. That's my understanding. Again, this requires a lot of very careful modeling that has not been done yet. That is being done. But yes, we are definitely thinking about this. But basically, we don't want to put a lot of work and delays into the sort of basically, we don't want to address this problem preemptively if it's not actually a problem. Because that one, that'll take a lot of time. It could delay the launch of general programmability, which is really important for the network in general. And we just don't have enough information to know if it's really going to be a problem.
You mentioned that there's the whole system is EVM agnostic, but is there a contract that you expect EVM to agree to, and what happens if they break that contract?
So right now we are deploying a built-in EVM. So this is the EVM people will use. It has a well-known code CID. So every actor in Filecoin actually has a code CID. So you don't have to compare the entire code. You just look at the CID and you know exactly what actor it is. In the future, once we have native actors, people will be able to deploy their own EVMs. Then it'll come down to actors to decide which EVMs they trust and which EVMs they don't trust. Is that approximately your question?
I think so. I think my concern was that because getting Ethereum integrated is huge, but it also creates this weird inverse dependency on if they change something.
Oh, I see. Sorry.
How does that affect us?
Yes. That's a very interesting question. So basically that will go through EIPs, and we actually haven't figured out the final answer to that yet. Basically, if the EIP is generally useful, we think it's useful, someone will make a FIP to import the EIP, and then we'll upgrade the built-in EVM. If someone deploys another EVM, one of the plans, this is not done yet because we're working at M2.1 and M2.2, but once we have native actors, the goal is to allow actors to upgrade themselves if they choose to, if they import the right syscalls with a bunch of security checks and all that kind of stuff. But that would allow an actor to decide to upgrade itself to a new version of the EVM. This would be sort of a choice by the actor itself if they decided to need the feature. Honestly, it's probably not necessary though, because what you can usually do is you just deploy a new version of the EVM. Because if you have an old actor that doesn't support this feature, if you have an old EVM that doesn't support the feature, the code running in there is not going to be using the feature. So if someone introduces a new EIP that adds some feature to the EVM, okay, fine, you just say that new actors use the new EVM, old actors use the old EVM. It doesn't really matter too much.
So now, if we bring the EVM and VM on the table, again, I just want to figure out, now we know about the smart contract language like EVM Solidity and then Move, and then also Near is using Rust, and we are going to use Rust. So my question would be there are so many language, and there are developers not just coming from Solidity community. And if I put on the table, here, this is FVM, this is FEVM. I'm not sure what's the pro and concept for them to choose what's the better option to go and then to develop on Filecoin.
Well, okay, so that is actually a very good question as well. So for M2.1, so February next year, the answer will be FEVM, because that's the only one they have. They can't deploy native contracts. After that, it does become trickier. Basically, the answer is there will be a lot more tooling for the EVM, at least at first. So if they want to use the thing they're familiar with, they use the EVM. If they want something that will probably have better performance and better gas usage, native contracts will probably be better in that way. At the end of the day, it shouldn't, we're working very hard to make sure we don't have split ecosystems. We're adding a couple of opcodes to FEVM that allow you to basically send and receive sort of messages in native formats and handle native method numbers. And you will also be able to basically just implement the EVM method number in your native contract. So you'll be able to send and receive that way. We're also working on different calling conventions and ways of describing these things. These probably won't completely land by M2.1, but we hope to have them all in place by M2.2. But yeah, basically the goal is to not have like the EVM ecosystem and the native ecosystem. Instead, is to have just the ecosystem where you can kind of call back and forth between them.